Hey everybody in Honors Pre-Calc, welcome to lesson 4.1. This is the beginning of several units that all have to do with trigonometry. So I wanted to just kind of step back and take a look overall at our units for the year before we dig deeper into this. So we've already finished units 1 through 3, which are all in different ways kind of review of Algebra 2 with maybe a few new components, right? So we're getting into unit 4 now, which is an intro to trig. And this unit takes a look at trig, which is sine, cosine, and tangent and everything that has to do with those trig functions. But it kind of breaks it down into right triangle trig, or in general, just triangle trig, and then circle trig. So we'll end up looking at the unit circle. And some of this, as a lot that we've already done, is going to be reviewed for some of you, but with a few new components. Then once we kind of are mostly comfortable with triangle and circle trig in unit 5, we'll take a look at trig graphs, like what happens if you graph y equals sine of x on your graphing calculator. We'll take a look at that. And then we're going to get into trig identities, which is just a fancy way of saying an equation that we can use over and over in different contexts, similar to a formula. And we're going to verify and talk about different trig identities. So equations that have sine, cosine, tangent in them. What does that look like? How do we solve those? That type of thing. So that's kind of going to be our next few months. I know we've been going fairly quickly through units 1, 2, and 3. We are going to get a little slower, especially when we get to units 5 and 6. But for now, we're going to start with what you probably are most comfortable with when it comes to trig, which is right triangle trig at the moment. If you remember SOHCAHTOA, that's what we're going to be focusing on today. Okay, so I want to pull up our overview. And here's what we're doing. So students will determine the sine, cosine, and tangent values for 30, 45, and 60 degrees using special right triangles. Yeah, we will see special right triangles today a little bit. And students will use right triangles to evaluate trig functions. We're going to be focusing more on this one, though. The essential question is, how can the definitions of trig ratios be used to help find their function values in a right triangle? You should already know what a right triangle is, right? It's a triangle with a 90-degree angle. And you should know basic properties of angles and side lengths of triangles. For example, a right triangle has one 90-degree angle. The three angles add up to 180 degrees. And the side lengths follow the pattern a squared plus b squared equals c squared, if c is the hypotenuse. Here's an example of a question you'll be able to answer. A surveyor is standing 115 feet from the base of the Washington Monument. He measures the angle of elevation to the top of the monument at 78.3 degrees. How tall is the Washington Monument? Round to the ones place. So we'll be able to solve questions like that by the end of this lesson. All right, so I'm going to switch over to the notes so we can get started with some math. Okay, here's our notes sheet for 4.1, right triangle trig. And we have 6 trig functions that we're going to be studying today: sine, cosine, tangent, cosecant, secant, and cotangent. And I want you to get very familiar and accustomed to when you speak these out loud, saying them like that, right? We're not going to say sin or cos or tan. We're going to say sine, cosine, tangent, cosecant, secant, and cotangent. All right, you can even write those down if you want. This one is sine. This is how you kind of spell them out. And then we have cosecant, secant, and cotangent. All right, so a couple things. On the right side of these equations or these formulas, we have kind of the side lengths in a right triangle. So if our right triangle looks like this, we always have one angle that's not the right angle that's labeled as theta. That is a Greek symbol. It's spelled T-H-E-T-A in English, but it's pronounced theta. And so theta is some angle that's not the right angle. And we have three side lengths, and they're referred to as either the opposite side of the angle, so that's straight across the triangle. We have the adjacent side, which is the angle directly next to, the side directly next to the angle. And then the hypotenuse, which is always across from the right angle. And so the sine of this angle is going to be the ratio of the opposite side over the hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then cosecant, secant, and cotangent are reciprocals of sine, cosine, and tangent, respectively. How I usually remember this is that tangent and cotangent go together. That makes sense. And then for the other pairs, there's always one trig function that has the prefix co. So sine goes with cosecant, cosine goes with secant. And to remember the first three, sine, cosine, and tangent, you've probably heard before. So, ka, toa. And SOHCAHTOA is just kind of a mnemonic device that helps you to remember that sine is opposite of sine is opposite of hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. SOHCAHTOA. I use that. Most people will use that regularly to help them remember these things. Okay. There are a few more identities or formulas in this notes sheet. We are not going to be using all of these today, but I just wanted you to start to see that we have these things called identities, especially these Pythagorean identities down here that we're going to be using a lot in future lessons and units. You have reciprocal identities, co-functions, and quotient identities. And we're not going to dig too deeply into that, but I just wanted you to see that there's going to be a lot of formulas that have trig functions involved. But let's just skip down to example 1. Take a look. So in letter A, we have a right triangle with two sides labeled, and we have one angle labeled as theta. So we're going to find the value of the 6 trig functions as ratios of theta. So first thing we can do is identify our missing side length. And remember that a squared plus b squared equals c squared. So that would be 9 plus 16 equals c squared. So 25 equals c squared. So the hypotenuse is 5. That's a Pythagorean triple, right? When you have 3 side lengths that are all whole numbers. So this is a 3, 4, 5 right triangle. That's called a Pythagorean triple. If you wanted to write that out, we could write that is the formula that makes c equal 5. So that's what that goes right there. But to answer this question, we're going to have to find all 6 trig functions. So we're going to have sine, cosine, tangent, cosecant, secant, and cotangent. All right. So sine is the opposite over the hypotenuse, or 4/5. The cosine is the adjacent over hypotenuse, or 3/5. Tangent is the opposite over adjacent, 4/3. And if you have this lined up properly, cosecant, secant, and cotangent, remember, are just the reciprocals of those answers. Okay. So right now you might be thinking, what is going on here? Why is this even necessary? All we did was write the sides as fractions. How is that helpful in the future? So sine, cosine, and tangent, and cosecant, secant, and cotangent are functions that actually allow you to find the measure of the angle. So we can use this information, given that this is a right triangle, we can find the value of this angle using the function. And we don't have, sine, cosine, tangent memorized, but our calculator can do the work for us and tell us the value of the angle. And we'll get into that as we move to the back of this sheet. But actually, why don't we just try one right now? So the first thing you're going to want to do is change your calculator into degree mode. So if you press the mode button right here, and we're going to go to where it says radian and degree, and you're going to want to change it to degree mode. That'll give us answers as degrees instead of radians. That's 2 different ways to measure angles, but we're more interested in degrees when we have triangles. So we're in degree mode. If we have a function like this or an equation like this, sine of theta equals 4/5. And I'll write this under here. If sine of theta equals 4/5, then we can do the inverse sine of both sides to find the value of the angle. So it'd be second sine gets us the sine inverse like this, and we put in the fraction. So this is 53.13 degrees. Okay, so anyone who works in construction or any career where you have kind of different side lengths and angles to worry about, they're gonna legitimately be using trig, sine, cosine, and tangent to find angles and side lengths for their job, okay? And so we just found that the measure of this angle right here is 53.13 degrees, which would be extremely important if you were constructing a building based off of this diagram, right? All right, letter B. Let's take a look at this one. We have two sides given, 1 and 1, and theta is this angle right here. Well, first of all, we can find the measure of the angle. We have a 45-degree angle and 90-degree angle given. So 180 minus 90 minus 45 is 45, but that's not the answer to the question. The question is, find sine, cosine, tangent, cosecant, secant, and cotangent. So in order to do that, we're going to need all three side lengths. So 1 and 1. And if you remember from algebra 2, you might remember that this is a special right triangle and the side lengths are in the ratio 1, 1, radical 2. But if you don't, you can use the Pythagorean theorem. 1 squared plus 1 squared has to equal c squared. So c is going to be the square root of 1 plus 1. And we are ready to write out our ratios. Notice how I'm writing the symbol theta. I kind of do the outer circle and then keep my pen on the paper and draw the line across. That's a standard way for mathematicians to write theta. You wouldn't write like a circle and then draw a line through it, although that would still be a valid way to do it. That's just not usually what you'll see. Okay, and now we're going to write this out. So we're going to start with sine. Sine is opposite over hypotenuse, so it's going to be 1 over root 2. However, you might remember that we don't want to have a square root in the denominator of a fraction if this is going to be simplified. So we're going to multiply by root 2 over root 2 and end up with root 2 over 2. Hopefully that makes sense. Root 2 times root 2 is 2 because it's the square root of 4. Cosine is going to be the adjacent over hypotenuse, which is the same thing. So again, we're going to simplify the radicals that were in the denominator to get this. And tangent is opposite over adjacent. So that's 1 over 1. So we'll just get 1. All right, now we're going to flip these fractions. So over the cosecant, if we flip this fraction, the square root's going to be in the denominator. I'm just going to go back to the original form, which was 1 over root 2, so that we can avoid having to simplify the radicals again. So if we flip 1 over root 2, we'll get root 2 over 1. For secant, if we flip 1 over root 2, we'll get root 2 over 1. And for cotangent, we flip 1 over 1 and get 1 still. Okay, so there we go. Let's look at letter C. So now we have another special right triangle, which is a 30, 60, 90 triangle. You might remember that from algebra 2 as well. That's our two types of special right triangles. We got the 45, 45, 90 and the 30, 60, 90. And you might also remember that the way that this special right triangle works is that the side lengths are in a ratio 1 to root 3 or 1 to radical 3. Sometimes you would say x, 2x, and x root 3. But again, if we didn't know that, we could write it out using the Pythagorean theorem. So we have 1 squared plus plus b squared equals 2 squared, right? If we think of this as a, this was b, which we didn't know yet, and this was c. We start to solve for b, so we get b squared equals 4 minus 1. So b is root 3, and since it's a side length of a triangle, we're leaving it positive. Okay, so now we're ready to write out our sine, cosine, tangent. And our cosecant, secant, and cotangent. And let's think this through. So for sine, sine is opposite over hypotenuse. So it's root 3 over 2. Cosine is adjacent over hypotenuse, 1 over 2. Tangent is opposite over adjacent, root 3 over 1, which I'm just writing as root 3. Cosecant, secant, and cotangent will flip these. So for 2 over root 3, for root 3 over 2, it flips to 2 over root 3, which will equal 2 root 3 over 3 when you simplify. For secant, we flip 1/2 and get 2. For cotangent, we flip root 3 to get 1 over root 3, which will equal root 3 over 3. All right, last one over here. You can see that this is actually the same triangle. So it's the same 30, 60, 90 special right triangle, but the theta moves. So instead of theta being 60, now we're thinking of theta as being 30. So let's see what happens to our trig functions. All right, so for sine, now we're situated up here. So opposite over hypotenuse is going to be 1/2. Cosine adjacent over hypotenuse is going to be root 3 over 2. And opposite over adjacent is going to be 1 over root 3, which is root 3 over 3. And now we flip all of those for the other side. So 1 over 2 is going to flip to 2. Root 3 over 2 is going to flip to 2 over root 3, which is the same as 2 root 3 over 3. Cotangent, I'll start with that first fraction and flip it to root 3 over 1. All right, I want you to take a second then, once you write that down, to compare the answers from C to the answers that we just came up with in D. You're going to see that they are very similar. They relate to each other, right? The sine and the cosine switched. The cosecant and the secant, therefore, also switched. And the tangent and the cotangent switched. So in these two scenarios, the trig functions that share part of their name actually switch. So sine and cosine, secant and cosecant, and tangent and cotangent. Those pairs actually switched. And that's part of the complementary angles piece up at the top. So if we have sine of 90 minus theta, that's cosine of theta. And the same is true for the cosine and the tangent. I'm realizing I wrote the same exact thing twice here, didn't I? These ones were supposed to be the secant, the cosecant, and the cotangent, kind of in the opposite direction. But does not matter. In any case, all the way back down here, what that means is, think about that, theta being here versus theta being here in the same triangle makes those complementary angles. Complementary angles add up to 90 degrees. So 60 plus 30 equals 90. And it's all about just kind of the sine and cosine switching, because sine in this situation was opposite over hypotenuse. Cosine in this situation is adjacent over hypotenuse, but that's pointing to the same side over the same side, right? Root 3 over 2, root 3 over 2. So you can kind of see that if we move theta, all that's happening is we're switching what order we compare the sides in, and so the trig functions are just going to switch around. All right, that's what's going on there on the front. We're going to flip on over to the back here then and try some more. So let's take a look at example 2. Letter A. The sine of theta equals 0.6 for a given theta that is an acute angle. Acute meaning less than 90 degrees. Find the values of cosine of theta and tangent of theta. All right, so for this situation, we are going to kind of sketch out a sample of what this right triangle might look like and label one of the angles as theta. We're given that the sine of theta equals 0.6, but really it's going to be way easier to manage if we think of this as a fraction, because that's really the way that the trig ratios work. So 0.6 means 6 over 10, which I'm going to reduce to 3/5. And 3/5 is going to represent the opposite over the hypotenuse, because that's what sine means, right? Sine is opposite over hypotenuse. So if we kind of think of that in terms of this right triangle that we sketched down here, the opposite over the hypotenuse are going to be 3 and 5. And now we have a question that's very similar to the ones on the front. So once we have that set up, we first want to think about, okay, what is the missing side of this right triangle? And if you use the Pythagorean theorem and think of this as b, you're going to get 3 squared plus b squared equals 5 squared. So we have 25 minus 9. So b squared is, what, 16? So b is going to be 4, right? Because that's a 3, 4, 5 right triangle. Again, it's positive because we are working with side lengths. So they're always going to be positive. Okay, so now we want to think about what is the cosine and the tangent of this angle. And we're just going to use SOHCAHTOA to help us solve that. So cosine is the adjacent over the hypotenuse. And now that we have this triangle sketched, it's really not that bad, right? It's just 4 over 5. Tangent is going to be the opposite over adjacent, or 3 over 4. And that answers the question. Okay, let's take a look at letter B. The tangent of theta equals 3 for a given theta that is an acute angle. Find the values of cotangent and secant. So again, I'm going to draw a right triangle for this scenario. And tangent is 3. So I'm going to think of that as 3 over 1, so that it's in fraction form. And tangent is what? Opposite over adjacent. So that means we have the opposite side is 3 and the adjacent side is 1. It's very clear now to me that this right triangle is not a good diagram because 3 should be 3 times as long as 1. But a rough sketch is all we need for this. We don't need to be perfect, so that's perfectly fine. So now that we have that, we can find the missing side. 1 squared plus 3 squared has to equal c squared. So we have what, 9 plus 1. So 10 equals c squared. So c is going to be the square root of 10. And so we want cotangent and secant. So let's think about how that works with our right triangle. Cotangent is the reciprocal of tangent. So cotangent is going to be adjacent over opposite, which will be 1 over 3. We didn't even need to find the root 10 in order to solve that one, right? Tangent was the cotangent is the reciprocal of tangent, so we just flip that and we get it. But let's try secant. So secant is hypotenuse over adjacent, and that's because it is the reciprocal of cosine. And so we have the hypotenuse over the adjacent, which was 1, so it's just root 10. Okay? So that's our 2 answers to that question. All right, moving into example 3. We can evaluate trig functions with the calculator. I already showed you a little bit of that. We kind of evaluated the opposite of a trig function, but you can evaluate trig function just by pressing sine, cosine, or tangent. So if we did the sine of 53.1301235 that we just found in that earlier question, you'll end up with something very, very close to 4/5, right? Because you take the sine of the angle, you'll get the ratio. Okay, so let's try this one. This is an interesting question because it has the secant of what we are going to read as 5 degrees, 40 minutes, and 12 seconds. Degrees, minutes, seconds is a way to break down degrees in smaller pieces without using decimals. It is occasionally used with latitude and longitude measured in degrees, but it can also be used in this context. And the minutes and the seconds break down a degree in the exact same way that they break down an hour. So there are 60 minutes in a degree, and there are 60 seconds in a minute. So if we're going to translate this into just degrees, or convert, which we'll do first. So we're going to convert to degrees. We're going to end up with 5 plus 40 over 60 plus 12 over 60 times 60. So this is translating the minutes into degrees, and this is translating the seconds into degrees by doing 60 seconds per minute and 60 minutes per degree. So if we combine all of this, we'll get 5.67, and that is the same value as this. So we could write it as 5 degrees, 40 minutes, 12 seconds equals 5.67 degrees. It's kind of like if you say somebody is 5'6", so they're 5 feet 6 inches tall. You could also say that they're 5.5 feet tall, right? Because 6 inches is half a foot. So it's the same idea. We're just chopping off or getting rid of the smaller units and changing it all into the bigger units. All right, so now we are going to actually calculate this answer. So to find the secant of that, which we're now going to think of as 5.67 degrees, secant is 1 over cosine. So in our calculator, we can type that in as 1 over cosine of 5.67 degrees, because our calculator doesn't have a secant button. But secant's the reciprocal of cosine, so this will work. So on our calculator, we're going to type in 1 over the cosine of 5.67. Notice I'm in degree mode, so I don't even have to put the degree symbol. It's already assumed since we're in degree mode. I press enter, so we get 1.0049. And that answer might not mean much to us, but what it really is the ratio of what the secant. So it's the ratio of the hypotenuse over the adjacent side of a right triangle that has this angle in it. Okay? All right, let's look at example 4. Solving a right triangle. A surveyor is standing 115 feet from the base of the Washington Monument. He measures the angle of elevation to the top of the monument as 78.3 degrees. How tall is the Washington Monument? Okay, so let's try this. We've got my best sketch of the Washington Monument. And some little dude here is standing 115 feet from the base. He measures the angle of elevation to the top of the monument as 78.3 degrees. How tall is the Washington Monument? So we want the height, or the H, of the Washington Monument, given this length and this angle. And this is another way that trig is used in the real world, right? With a surveyor. Okay, so let's see if we can figure this out. Without actually kind of getting up there and measuring with a yardstick the entire Washington Monument, we can figure out the height just by using these two pieces of information and a right triangle. So we're gonna have a kind of a right angle down there. So let's see what we got. We are looking for the opposite side in this right triangle from the angle that we know, and we are given the adjacent side. If you think about SOHCAHTOA, the question is, which of the 3 trig functions deals with the opposite side and the adjacent side? And the answer is tangent. So that's how we pick to use tangent. So we're going to have tangent of theta equals opposite over adjacent. That's the initial formula. and we can plug in what we know. So we know that the angle is 78.3 degrees. The opposite we're calling H, and the adjacent we're calling 115. So H is going to equal 115 times the tangent of 78.3 degrees. And that's what we're going to type into our calculator right now. So we got 115 times tangent of 78.3 degrees. And we get 555.31. It's said to round to the ones place, which is the nearest whole number. So we get 555 feet. All right, pretty cool. All right, letter B, find the length C of a skateboard ramp given the height of the ramp is 4 feet and the acute angle between the length and the base is 18.4 degrees. Okay, so if we sketch this ramp, it's gonna look like a right triangle. And the height of the ramp is 4 feet. The acute angle between the length and the base of the ramp is 18.4 degrees. And we want to know C, the length of the ramp. So based on the fact that we were told the angle between the length and the base is 18.4, you can tell that in this triangle, we're referring to this side as the base and this side as the length. So the length we're calling C. We want to find C. So think about SOHCAHTOA. If this is our angle that we're referencing here, we have the opposite side and we're looking for the hypotenuse. Opposite hypotenuse are sine. So we're going to be using sine equals opposite over hypotenuse. Theta is 18.4 degrees. The opposite side is 4 and the hypotenuse is C. So we're going to try to solve this for C. I would start by multiplying C to the other side because it's in the denominator right now. And then let's divide by the sine. So we have C equals 4 over the sine of 18.4 degrees. And if I type that into my calculator, you're going to get approximately 12.67 feet. That's how long the hypotenuse of the ramp is. All right, that was the last question in the notes. When you get to the worksheet for this lesson, I just wanted to point out that for questions 4, 5, and 6, we're talking about right triangles here, and certain angles and side lengths are given, and then there are blank triangles. I'll tell you right now that for each of these, it is assumed that angle C is the right angle. So you can go ahead and sketch that in, and that'll help you make sure that you know how to label your answers. Okay, so there's one extra angle that's always already given. Angle C is 90 degrees. Okay, that's kind of goes along with the Pythagorean theorem, right? Because the Pythagorean theorem says that a squared plus b squared equals c squared. It's referring to side lengths, but the side that's the hypotenuse is across from the right angle. So that's how you can set those up. It doesn't matter where you put A and B. You can switch A and B. It's just a rough diagram, so it won't change your final answers. All right, everything else hopefully makes sense. On the back, same idea. Angle C is always going to be the right angle. It doesn't matter where anything else is. But that's the end. So thank you very much for watching. Let me know if you have any questions. Good luck with the worksheet, and I hope you have a great day.